Well, we're going to continue talking about increasing, decreasing concavity and how that relates to our first and second derivatives. What we found out last time is that the first derivative is going to give you increasing or decreasing, because if the slope is positive, you're increasing. If the slope is negative, you're decreasing. We also found out about the way the curve is shaped. So basically, how we're increasing or how we're decreasing is also important. And what that was called was concavity. Can you tell me which one of these is concave up, the left or the right?
Left.
So this was the concave up, and this was the concave down. And here's what we determined. The second derivative, which is the way the slope is changing, if the slope is increasing or the slope is decreasing, will tell you whether we're increasing at an increasing rate, or increasing at a decreasing rate, or decreasing at an increasing rate, or decreasing at an increasing rate. So basically, how we're shaped. So here's what we say. If the second derivative is positive, what that means is the slope is increasing. If the slope is increasing, that means we're going to be concave up. Notice what the slope is doing. The slope is increasing. Does that make sense? So if our second derivative is positive, the second derivative says the slope is increasing. Remember, the second derivative is the rate of change of our slope. You with me on this? The first derivative was the slope. The second derivative is the rate of the change of the slope. Basically, if your slope is increasing or decreasing. So it says the slope is increasing, that's going to give us a concave up. So this means concave up. If our second derivative is negative, that means the rate of change of our slope, how our slope's changing, that means it's negative. That means that the slope is actually decreasing. The slope is decreasing, slope is positive, slope becomes zero, slope is negative. That gives a concave down shape. I did explain all that last time, right? Okay, good. What would happen if the second derivative equals zero? Well, right now we have a question mark about that. But here's what we're going to fill this out as. If the second derivative equals zero, that means the rate of change of the slope is constant. That means we don't know what's going on right there, but it could possibly be where it changes from concave up to concave down, or concave down to concave up. Do you remember what that point was called?
Inflection point.
This is a possible inflection point. There's cases where it's not, but it's possibly an inflection point. Or pip. Pip. Let me review just a couple things with you. Let's give a couple graphs here. Do you have any inflection points on this graph?
Yeah.
Could you tell me where it's concave up and where it's concave down?
Left and right.
What am I starting out with? Concave up or concave down? Notice how concavity really doesn't have much to do, well, it does have to do with increasing and decreasing, but you can be concave up even though you're decreasing and increasing. Do you see what I'm talking about? Here we start decreasing and then we increase, however, we're concave up the whole time. Where the concavity has to do with the slope, the way the slope is changing. If the slope is increasing, that means we're concave up. So we're concave up. Tell me where to stop being concave up. Right in here? Somewhere in there, yeah, for sure. Somewhere in there where we stop being concave up, and we start being concave down. We start being able to hold water and have something that doesn't hold water. Where do we stop being concave down? Somewhere in here. It looks like about right there to me. And then we're concave up for the rest of our curve. Those 2 points, those are called our inflection points. So right here, this is how this would relate to this information. These are our inflection points. Let's look at the concave up. It says the second derivative should be positive. The second derivative says the slope should be increasing. Is the slope increasing here?
Yeah.
Not the function, the slope. Is the slope increasing here?
Yeah.
Sure, until it gets to that point. Guess what happens at that point? It stops increasing and it starts decreasing. In other words, our slope hits a peak and starts falling back down. That's what that says. Now our slope is decreasing, 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 till it hits that point and then starts increasing again. At those inflection points, that's what's going to happen, is where your second derivative equals 0. How many people have an okay understanding of our concavity and the inflection points? Now, I'll get more specific on how you actually find those later, okay? Would you be able to give me intervals of increasing, decreasing, concavity, and any inflection points that occur? Would you be able to do that for me?
Yeah.
Can you tell me where we're increasing? Let's write that out. Increasing, decreasing, concave up, concave down, and any inflection points. Where are we increasing? Give me an interval where we're increasing. The function needs to be going up from left to right. Where are we increasing?
Right.
So all the way from the start of our graph, which, I mean, this goes way down, but it could start ultimately from negative infinity. It increases all the way up, it's going up until we reach x equals what?
3.
0.
X doesn't equal 3. X actually I'm not talking
0.
about that. I'm talking about where's the function stop increasing? Where's it stop going up? On the x-axis, where's it stop? Okay, so when I say from negative infinity, here's what I don't mean. Some of you are a little bit shoddy on your graphing. Negative infinity doesn't mean I start down here. That's not what negative infinity on the x-axis means. X-axis is this way, right? It says from negative infinity, I'm increasing all the way till I get to this point, which is 0. Do you see what I'm talking about? The function is going up. I don't care where the function stops, but on the x-axis, right there, it's increasing from negative infinity to 0. Are you okay with that? So not the height of the function, where it's increasing on the x-axis. Does it pick up again and start increasing?
Mm-hmm.
Where at? X equals what?
2.
So from 2 to where?
Lost infinity.
From 2 to infinity on the x-axis would be another interval of increasing. Are you okay with the negative infinity to 0 and then the 2 to infinity? Nudge your head if you are, feel okay with that. Okay, so we're not talking about this way, we're talking about what the function's doing as we're going along the x-axis. Give me decreasing. How many intervals do we have that are decreasing?
1.
From where to where?
0 to 2.
Yeah, if we're not understanding this, what some people say is from 3 to negative 3. Is that our period of decreasing? No. That would be the range that we're decreasing from here to here. But what I'm talking about is the function is decreasing on the x interval from 0 to 2. Do you see what I'm talking about there? Yeah or no? Are there questions about that? You guys dead today? I see a lot of that.
Seems counterintuitive not to say negative 1 to 0.
Negative.
Increasing, or at that point where it crosses the x-axis the first time on the left.
Right here?
Yeah.
But we're still increasing from here as well.
Oh, so it slowly will eventually go.
We always read from left to right. So we're saying when we start this function at negative infinity, because it never ends, when we start this function, it's automatically starting to go up. And it keeps going up and keeps, look at, as I'm going, like a timeline, right? Keeps going up, keeps going up, keeps going up, keeps going up, going up, going up, going up, going up, going up, stops. Going down, going down, going down, going down, going down, going down, stops. Going up, going up, going up, going up, going up, going up, forever, forever. Do you see what I'm talking about? Have I drolled you into a state where you're almost sleeping now? Yes? Good. I'm glad Glad that's you.
2 hours of sleep.
Hey, me too. All you have to do is sit there. Think about me. Come on. Selfish people. 0 to 2 is decreasing. If you need more help on that, you come and see me. How about concave up? You need to be able to determine concave up to concave down. Am I concave up here?
No.
Concave up? Concave, how about here? Concave up. This is concave up?
No.
This is right here?
No.
Where does it start?
Right there.
Ah, concave up, concave up, forever. Concave up from 1 to infinity. Concave down, let's start that. Remember, it has to go in order of a number line. Where do we start being concave down? Remember, you're talking about the x-axis. The x-axis. Where do you start being concave down? Up till what point? 1. This is all concave down until you get to here, right? X-axis says negative infinity to 1. Is there an inflection point? If you change concavity, you have an inflection point. What is it at? 1.
0.
Does it change concavity here?
Just that one.
Does it change concavity here? No. X equals 1, or the point 1, 0. I know the notation kind of sucks because we don't have different notation for intervals versus points. That's an interval. That says from 0 to 2 non-inclusive, from 1 to infinity non-inclusive, negative infinity to 1 non-inclusive. That's a point, 1 to 0. Okay, that's an actual specific point. I know our notation's horrible because points and intervals look the same for some numbers, but this is a point. Those were all intervals. But you have to feel okay with our intervals of increasing, decreasing. Iffy, stick with it. We'll talk about one more. You'll get practice on it on your homework as well.
Sure. Leave that out.
Absolutely. How about this? Let's see if you kind of really understand what you're doing here. By the way, were there any questions on that before I move on? I saw some people who weren't really quite grasping the whole why we have these numbers, but you have to. Think that this is all on the x-axis. You're not talking about the heights of the actual function. You're talking about where it's increasing, decreasing. So you're not going to have a 3. You're not going to have 3. You're talking it's going into increasing until x equals 0. Then it stops increasing. It's decreasing from 0 to 2. Then it starts increasing again from 2 to infinity. And that's what we're talking about. And that's how you determine those intervals. Does that make a little bit more sense? Hopefully. Now, at each point, here's what I want to do. I want to determine whether our first derivative and second derivative are positive or negative. That's what I want to do here. So let's take a look at it. Let's look at point A. I'll help you out with point A, and then the rest of it I want you to do on your own. Just practice it. On point A, I want you to look at our first derivative. The first derivative means slope. The first derivative says whether I'm increasing or decreasing. Remember that? First derivative says increasing or decreasing. If the first derivative is positive, I'm increasing, going up. If the first derivative is negative, I'm decreasing, going down. So let's look at very carefully, very slowly. Let's think about the first derivative at A. Is my function climbing or falling at the point A? Is that increasing or decreasing? Decreasing. So should this be positive or negative? Negative. The first derivative will be negative there. Definitely negative. It says that my slope is negative. My slope's less than 0. That means I'm decreasing. Do you follow me? Now, let's think about the second derivative. At the point A, the second derivative
Increasing.
says whether my slope is changing
Concave up.
positively or negatively. Is it my slope is increasing or my slope is decreasing? So think about this. Is my slope getting gradually bigger or getting gradually smaller? So then my slope is increasing. Do you follow me? My slope is increasing. Also, that means I should be concave up. Am I concave up right there? For concave up, is that positive or negative? The second derivative will be positive. It says my slope is increasing. My second derivative should be positive. Do the rest. Do B and C. All right, so let's go for it. At point B, if I'm looking at point B, my function's increasing. My slope is positive, so this should be positive. At point B, well, that's almost at the cutoff, but it's still, the slope is still a little bit
not at the
increasing
cutoff.
right there. So at point B, we're still increasing. This should also be positive. Did you get both of those positive? It's increasing and it's concave up. That's how you can view that as well. Point C. At point C, my function is decreasing, my slope is negative, that means my slope is negative, that's certainly true. And also, my slope is getting gradually less and less and less. So my slope is decreasing as well. If my slope is decreasing, that's also negative, concave down as well. How many of you got both those right? Good for you. If not, notice where your mistake was. Was the first derivative or second derivative? First derivative is increasing, decreasing. Second derivative is concavity. Decreasing, concave up. Decreasing, concave up. Increasing, concave up. Increasing, concave up. Decreasing, concave down. Decreasing, concave down. That's the same exact language, or same exact idea that we just talked about. Now, the next thing we're gonna start getting into is relative extrema and how that relates to graphing polynomials. So let's look a little bit about what relative extrema means. It's not. It's not. Here's what relative extrema means. It means a relative max or relative min. You've heard that before. Just to refresh your memory, a relative max is basically the idea of a high point on an interval. It doesn't have to be the highest point on the graph, it just has to be the high point on a little interval.
So not the peak, but
It is a peak.
it is a peak?
It's a peak for an interval. Not the absolute,
okay.
not the absolute max necessarily, but it is for an interval. The high point. Here's a better definition. A relative max happens when a function changes from increasing to decreasing. That should make sense to us, right? From increasing to, from increasing to decreasing, we should have a peak. That's a relative max. It doesn't have to be the highest point on the graph, but that's the definition for relative max. So the high point, that's kind of an old old definition, that's not very mathematical. This is where a function changes from increasing to decreasing. You know what? Relative min has basically the opposite definition right there. A relative min is going to be a low point in an interval. In other words, it's going to be where you change from decreasing to increasing. That should make sense, right? If you go from decreasing to increasing, you're going to have a little valley, a low point. So dot, 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 where the function changes from decreasing to increasing. Very quick examples for you, just so you have a little look at this. Would you be able to find me my relative extrema here? Relative extrema happens where you are changing from increasing to decreasing or decreasing to increasing. So stop me when I get to relative extrema, okay? Here, no. No, because we're not changing from increasing to decreasing, okay? You have that's part of our definition. So we're going to start here, no. Where do I get one? There. What is this?
Relative max.
Relative max, very good. Relative max. Is it the absolute max? No. Is it the highest my function goes? Mm-mm. That would be, right? That would be. How about, let's keep going. What else? There. Here, that's a relative min. Relative min. Keep going. This one? There. Yep. That's another relative max. And then there, that's another relative min. And then, how about this one? Yeah. Even though it's an absolute max, which we'll talk about later, it can still be a relative max, no problem. We have 3 relative maxes, we have 2 relative mins in this problem. Do you understand the idea of a relative max, relative min? Changing from increasing to decreasing for maxes, that gives us a peak. Decreasing to increasing for min, a relative min, that gives us a valley. My question is this. If this is a change from increasing to decreasing, or decreasing to increasing, that has to do with the slope, doesn't it? If the slope is positive, we're increasing, right? The slope is negative, we're decreasing, true? Well, what happens at a change from increasing to decreasing? What does the slope automatically have to do if we're going from increasing to decreasing? At some point between a plus slope and a minus slope, you have to hit what number? 0. You have to hit a 0. So what's happening to the slope as I'm getting to a relative max, as I'm getting to a relative min, max, min, max? What's happening to the slope at those points? Positive increasing, 0. Negative decreasing, 0. Increasing, 0. Decreasing, 0. So everywhere where we get a slope of 0, we're going to have a possible relative max, relative min. What we call those are critical numbers. So what's happening to the slope at a relative max or min? The slope is 0. So at all these points, note the slope is 0 for the relative max, relative min. The point at which a curve has a horizontal tangent, or in other words, the slope is 0, is called a critical number or critical point. That's a little definition. called a critical number. Okay, well, let's think about this for a second, all right? If your critical number is a place where your slope equals 0, do you understand the definition, firstly, of a critical number? Critical number is a place where your slope equals 0. Are they always relative maxes or mins? No, they're not. You can have other things that happen. So for instance, this curve. Do you have a point where the slope is 0? Yeah, but this is not changing from increasing to decreasing. It goes from increasing to nothing to increasing again. Just a different concavity. Do you see it? So that could give you a relative maximum, but it doesn't have to. That's the idea of a critical number. It's just a place where your slope is 0. So that's the idea of a So that could give you a relative maximum, but it doesn't have to. That's the idea of a critical number. It's just a place where your slope is 0. So if we're trying to find out where all of our slopes are 0 for a function, can you explain to me maybe the process of doing that? Let's pretend I give you a function and I say, I want you to find the critical numbers. What might you have to do to find the critical numbers?
Plug in 0 for the slope.
So the derivative gives you slope, true? If I take the derivative and I set it equal to 0, I'm going to find out all the places where all the critical numbers where my slope equals 0. Do you follow me on that? That's going to give me all my potential relative maxes and mins. That's the idea. So to find your critical numbers, we're going to take the first derivative and set it equal to 0.
Okay.
Take first derivative, set it equal to 0. You okay with that as well? One more side note. If you get a fraction, typically all you have to do is solve for zeros and set the numerator equal to 0, right? For this process, what we're going to learn is that for both the first and second derivative, I'm going to give you a first and second derivative test in a little while, like probably a week. But when you get there, you also have to check the points where the denominator equals 0 as well. So if you get a denominator, you must set that equal to 0 as well. That gives you undefined points for your slope. You need those, right? You need any undefined points for your slope. It's important. So little note, if you have a denominator, set the denominator equal to 0 as well. That could give you any undefined points for your slope, which would be a big deal. You can change from increase and decrease to undefined points. Let me prove that to you. Increasing, true? Decreasing, yes? Slope is undefined. You're going to change from increasing to decreasing at that point. Even though it's not differentiable, that gives you a point of changing from increasing to decreasing. Do you see what I'm talking about?
So denominator in the first derivative?
In the first derivative.
You set it equal to 0?
Yes.
Okay.
The denominator of the original function will just tell you where you're undefined. Now, a lot of times, that will match up. Okay, where you're undefined in the function is where you will be undefined for your slope. Most of the time that happens, but occasionally you get some weird stuff that happens. So you need to do both. Can we do an example to finally get away from all this theory stuff and really get into an example? Can we do that, please? Are you guys ready for it?
Yeah.
All right. So let's go ahead. Let's find the critical numbers. This. Find the critical numbers of that thing. What are we gonna have to do to find the critical numbers? Well, critical numbers involve slope, right? It asks where's the slope equals 0, so find the slope function right now. That means take a derivative. Go ahead, take a derivative. Derivative should be pretty easy. What's the derivative of this thing? Man, I'm a nice guy. Don't you see I'm a nice guy? I'm a nice guy. That's nice. That's nice. Why? Why is that nice? What are you going to have to do? That just gives you a slope, right? Because you just found the derivative. Derivative means slope. Our critical numbers occur where our slope equals what? 0. Set equal to 0. Solve it. That's going to give you the x values where your slope equals.
It actually said equal to 0. Not just the point 0. Yeah, because they give me a slope of -3.
Zero. Can you solve that? Yeah, it's like a piece of cake to solve. What are you going to do? That's what I'm a nice guy. You have options, really.
Add 3 divided by 3.
Square root with a plus and minus. That's going to give you plus and minus 1. Factor out 3 different squares, plus and minus 1. Either way, you can do that 2 ways, okay? So in either case here, x equals 1, x equals -1. Are those my points for my relative max and relative min? Those are my x values of my potential points for relative max, relative min. Are these, in this case, yes, this is going to be a relative max and a relative min. This one should go max min. Okay, that's what that should be. Now, we're going to talk all about that later. Right now, I'm just asking to find critical numbers. I'll show you how to determine that at a later time. Are you all right with that? Are these always giving you relative max and relative min? The answer is no. No, they're not. I've given you one example of that already. This right here is going to show up as a critical number. Is it automatically a relative max or relative min? No. So there's some cases where it's not. Okay, so you really do have to check on those. I'll show you how to check on them later, but they're not automatically relative max or relative min. We're going to switch gears just a little bit. We're going to move from relative max and min to absolute max and min. Now, what's absolute mean?
Highest point.
Yeah, absolute value would be like positive, always positive, but absolute means it's the most high or the most low. Relative, you're noticing this, we can have lots of relative maxes, right? Think about a sine curve. Oh my gosh, there's relative maxes all over that thing. Those all happen to be the absolute max for a sine curve, but they're all relative maxes as well. For the absolute max, it says, what's the highest number you attain, if any? Relative absolute max and absolute min means what's the highest or lowest value you attain throughout the whole. So we'll talk about that. We'll talk about how to determine it. It's not bad, so don't let it scare you. So when we talk about the absolute max, what we mean is the highest point on an interval, overall, the highest point that happens on that interval. Well, then that would mean the absolute min means the lowest point on an interval as well. Not one of the low points the lowest. That's what the absolute, how that differentiates from the relative. Relative could be, well, there's a few low points. Absolute minimum means the lowest. Absolute max means the highest.
Is that
Okay.
on an interval or on the function?
On an interval. Now the interval could be from negative infinity to infinity, but a lot of graphs don't have an absolute maximum on negative infinity to infinity. In fact, lots of polynomials don't. So we talk about on intervals as well. So some graphs don't have absolute max or min. On this interval. For instance, just think of an x cubed, okay? What's the highest point that attains? So can you say the number? Does it reach a peak? Ever? Do you know how much infinity is? Because I do. No, I don't. No, it's infinity. It never reaches an ending point, does it? It doesn't reach a highest point. It keeps going and going and going and going. Does it ever have a low point? The lowest point? No, this doesn't have an absolute max or an absolute min. How about this one? Does that have an absolute max? Max. Does it ever reach the highest point? No, it's infinity. Does it have an absolute min?
Yeah.
It's right there at 0, 0. That does have one. But so you'll see, and some curves don't have the absolute max or min on negative infinity to infinity. Some do. Most don't. Every polynomial doesn't have, it has one or the other, because polynomials go to infinity somewhere or another, right? They're never horizontally asymptotic, so you're always going to get one. So we like to distinguish between everywhere and then certain intervals. So an absolute max is going to be the highest point on an interval that you say it is. And the absolute min is going to be the lowest point on an interval that is defined for you, or that you say it is. Do you follow that logic there? Okay. Okay, so even though some graphs don't have an absolute max or absolute min on this, let me make a little suggestion to you. I'm going to suggest that every curve in the world has an absolute max and an absolute min on a closed interval. Would you agree with that? On a closed interval, so if I say from 3 to 2, there's going to be a highest point, there's going to be a lowest point, as long as the function is continuous. Yes? We don't want this idea. That would not. But as long as it's continuous, that's going to happen. So this, not so much. But every function has an absolute max and min, if the function is continuous, on any closed curve.
I swear you practice this at home. In front of your mirror.
On any closed interval. Open interval? Not necessarily. We'll talk about that in a bit. But closed interval, absolutely, yes. Okay, let me talk about one little piece of information you kind of need to know. Every continuous function, what that means is the function doesn't have to be continuous for the entire space of human existence. What it has to, or X existence, I guess, whatever. But it has to be continuous on that closed interval. Does that make sense to you? It's got to be continuous here. If it's continuous there, it will certainly have an absolute max, a highest point, and an absolute min, a lowest point. Do you follow me on that? If it's continuous for this part, it'll be there. Now, where might it exist? Where might that happen? Well, there's only a set number of points. If you think about it, if you think about it, that's a closed curve, true? Closed curve with my closed interval. Where could the absolute maxes and mins possibly occur? Well, they're either going to occur at a relative point, where I'm switching from decreasing to increasing or increasing to decreasing. It's going to happen either there, or it's going to happen at the end point. There's only two cases. It's either switching from going up to going down, that gives us a low point or a high point, or it's at the end where I would continue to go up, but I just chop it off and I go, no, you stop there, ha 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 ha. And then it has to occur there. Does that make sense to you? So it's either got to be at an end point or at a relative max or min. That means a critical number. So what's going to happen for your absolute max or min? For any closed interval, it must take place, you should be writing this. It must take place at either a critical number or an end point.
It's a lot of writing, this chapter.
This will occur at either a critical number or the endpoint. Can you raise your hand if you understand that logic? That it's going to be one of those two places. It's either going to be where a function changes from going up to going down to going up, or at one of the stopping points of our interval. Do you follow me on that? It's got to be one of those places, which means there's only a few points you need to check when you find an absolute max min. You're going to be checking your critical numbers by plugging them into your function, but you're also going to check your endpoints. We'll do some examples of that in just a second. And whatever's the highest one, that's your absolute max. Whatever's your lowest one, that's your absolute min. That's it. That's all we're going to have to do. This implies one more thing, though, kind of like a corollary. What if I don't have it closed? What if I have this?
It's going to be right before the
What if
end
it
pointer.
opened? Think about this for a second. This is an interesting case, okay? Check it out. Not check out my erasing, check out what I'm going to write after I erase. Check it out, I can erase really good.
Let's go.
If this is closed and the points are included, can you all see that the absolute minimum for this interval is right there? That happens at actually a relative min, where we change from decreasing to increasing. The absolute maximum is not this point, because there's a point higher. It actually occurs at the end point. You follow me? But now watch what happens if I say, ah ha ha ha. That would be this case, by the way, where you're closed. What happens if I say, no, no longer do you have those points? Now this and that. Where they're not included, that's this case. That's this case. Do you still have an absolute minimum? Yes, that point is the same. Do you have an absolute maximum? It's not here anymore, is it? Do you have an absolute maximum?
Yeah, be the point right
Think
there.
about the question. Does this ever stop getting closer? Let's say this level is 3. Okay, let's just pretend that's a 3. Does it ever get to 3?
No.
Does it get to 2.9? Does it
You
get
use the
2.99?
limit to define it.
2.999. 2.999. 2.9999999. Can you keep doing that forever and ever and ever? So do you ever reach an absolute max?
No.
No. No, you don't. Because you can keep getting closer and closer to 3. Between any 2 points, you can find an infinite number of points.
Yeah,
right?
that's true.
Between 2.999, however much you want to go, and 3, there's an infinite number of points that you can attain. So there is no absolute maximum here. What this says is that if you, listen carefully, if you've got a closed interval, you are going to have an absolute max and an absolute min if it's closed. Understand? If it's open, that means the absolute max and min must happen if they occur at a relative point, at a critical number. That's where they have to occur. If they don't occur there, then they don't exist at all. Closed intervals, you got both. Open intervals, if they were to occur, they would happen at your critical numbers. If they don't, then they don't exist. If they occur, they do so at critical numbers. Because there are no endpoints. Take away the endpoints here and they have to happen at critical numbers. Let me do one thing for you, okay? Let's fill out, let's say that this is no longer just open, let's say this one is closed. Does it change the fact that we have an absolute min, but we don't have an absolute max? Let's say that I open this one back up and I close that one. Does that change the problem? That now has an absolute max, and that's the idea. And you're going to be dealing with those type of intervals on your homework, where you're going to be finding your critical numbers, no problem. If they're closed intervals, you check your endpoints. If they're not closed intervals, you check your endpoints, but they don't have, you check your endpoints. You would still check this. You'd say, how high does that reach? How high does that reach? If it reaches close to 3, if I were to plug it in, if it reaches close to 3, well then that is bigger than this point, right? That means there is no absolute max. That means that, yeah, I get really close to that number, it's bigger than this one, but I never get there, therefore there is no absolute maximum. So for instance, if I asked you this question, find the absolute max between the interval of -1 to 4. And I ask it to you this way. If it's this way, they're both closed in. You follow me? Absolute min is here, absolute max is there. If I ask it to you this way,
Doesn't change.
absolute min is here, absolute max is there. If I ask it to you this way,
now there's no absolute max.
absolute min is here, absolute max is up. Doesn't exist. Why not? Because you'd say, well, if it were to exist, it would occur either here at a critical number or here at an endpoint. However, I don't have an endpoint. So all you have to do is this. This is what you would do. You would take this number, even though it's not an endpoint, you'd plug it in. You'd plug it into your function, and you'd say, is this value bigger than this value, function-wise? Because you're not going to have a graph. You're going to do this all with your functions. You'd plug it in. If this number, when you plug it in, is bigger than this critical number, the height of that, then you can't possibly have an absolute max because this one's going higher than that. That's what you're talking about. If you do this, nothing changes. Same.
So if you were to go on with the function to the right and come back down and then put like the open interval, would you?
Like right here?
Yeah.
You'd have an absolute max.
Okay.
Well, what do we say we do a couple examples?
Yeah, and then put like with the function to the right and come back down and then put like the open interval, would you?
Like right here?
Yeah.
You'd have an absolute max.
Okay.
Well, what do we say we do a couple examples here? We'll start one. Remember that clock's a little fast, so we start with time. So to find your absolute max and min, you find your critical points and you evaluate them. Critical numbers. And you evaluate your endpoints. Let me give you an example so that I can really flesh this thing out for you. That will end our day. Make everything nice and clear. Tell me the first thing you do. We're gonna do it very quickly. What do you do? Do it. That's your derivative. Did you get the same derivative? Oh, good. My derivative. Derivative hats on, taking right today. What do you do with that derivative, folks? You're setting equal to 0 because you want to find the place where the slope is equal to 0, right? That's your critical numbers. That's the only places where you could possibly go from up to down to up. So set it equal to 0 and factor and solve. What are you going to factor out of that? You're going to get x squared minus 5x plus 6 equals 0. You're going to continue to factor. You're going to get x minus 3. You're going to get x minus 2 equals 0. You're going to get x equals 3 and x equals 2. I factored that very fast, but I mean, that should be kind of no-brainer stuff. Are you guys okay getting the 3 and the 2? Are you sure? So here's what you check. These things right here are called your critical numbers. They are the only potential for going from increasing, decreasing, decreasing, increasing, your relative max and min. So what you check for sure your critical numbers, x equals 3, x equals 2, x equals, and x equals. What numbers are going to go here and here? 1 and 5. Very good. 1 and 5. Where am I getting the 1 and the 5? Sure. So 1, 5. Where do I evaluate those? The derivative is just going to give you zeros here. That's going to give you something worthless for those two. We're plugging into original function because the original function gives you heights. Do you understand?
Oh, okay. Makes sense. Two minus 15, 13, 23, 16, It's a horrible way of writing it. So absolute max and absolute min are at the endpoints, it looks like.
The original function gives you heights. We want to find out what's the highest and what's the lowest. Would you take those numbers, people on the right side, my right side, you people, plug in the first two, you people, plug in the last two. Make it quick, because we're running out of time. As soon as you get them, just yell them out to me for the 1 and the 2, and for the 3 and the 5. You guys have it easy. Whatever they are. I can't do it in my head. I'd probably do the 1 if I really thought about it, but I really didn't want to. 37? No, wait, no, way off. Minus 15. 23. This gives you a height of 23, true? This gives you what now?
28.
28, like it. Okay. What else? What's the 3? 3 and the 5. Come on, 3 and the 5.
The 5, I think, is 55.
The 5 is 55?
Maybe not. I think
55. Okay, 55. What's the 27 for this one?
What I did wrong there.
27? 27? Perfect. This is perfect numbers for us. Here is the explanation of absolute max and absolute min. You need to watch carefully. This is going to put everything together in your heads right now, okay? What's the largest number that is attained?
55.
That is now your absolute max. Your absolute max is not 5. Your absolute max is 55. It occurs at x equals 5. Does that make sense to you? The absolute max is 55. It occurs at x equals 5. That's the end point. You see how the end point comes into play for us. So this goes up and then stops. That was the picture I'd drawn earlier. What's the minimum value that's attained?
23.
Did they occur at critical points or endpoints? For this one, endpoints. Sometimes it'll be critical points. Let me make one more thing very clear to you, and then we'll stop for today. What if I had given you this?
And it couldn't have been
That.
the endpoint.
Listen, you do exactly the same thing. Exactly. Only when you plug this number in and you get the 55, can you actually get to the 55 that you are gone with the max. That's how that would disappear. This would only have an absolute min in this case. If I did this, you'd have nothing. No absolute max, no absolute min. How many people understood today? Okay, we'll do one more example this next time, then we'll continue. Okay, so right now we're in the business of finding absolute max and absolute min. And what we discovered from last time is that, well, let's see what you know about this. Is this going to have an absolute max and min, for sure? Why would you say that? If it's continuous, that's closed. So the absolute max or min, if this is continuous on the interval, will either be between that open interval or at an endpoint. So those closed endpoints dictate, if that's a continuous function, that we will have an absolute max and min. If I have them open, do we necessarily have to have an absolute max and min? No, not necessarily. It could go way higher than a relative max, relative min. So, and never actually get to that point. What's our idea of how to find an absolute max or min? What do we do first? That's like, if you don't know, just say derivative, and 90% of the time you're right. Because in calculus, the answer is derivative. In calculus 2, the answer is integral. So if you're falling asleep, you're like, Mr. Leonard says, what's this? You go, derivative. 90% of the time you're going to be right, okay? In Math 4B, it's integral. Yeah, you're right. That's not most of the class. So yeah, it's a derivative, but why?
Finding the slope.
Oh, good.
We're all asleep.
Very good. Okay, so what we're doing here is realizing that absolute maximums have to occur at either a relative max or relative min or at an endpoint. To find relative max or relative min, that's kind of hard to do right there. To find that, you find where the slope is 0. Change from increase and decrease, and that would give you those peaks and valleys. We evaluate all of the critical numbers and the endpoints, and that will tell us the highest and lowest. Find me the first derivative, please.
This can't be right. I don't believe it.
Okay, first derivative, if you do this, first derivative says you take down the 4/3, you can get 24 over 3, or you simplify as you go. Either way, you get 8 x to the, good, minus, perfect, very good. How many people were able to find that? Good for you, all right. Now, what do we do with that? Good, because that is my slope. I want to find out where I have a horizontal tangent. That's the potential places where I could be switching from increasing, decreasing, or decreasing, increasing. Potential places, and we'll check that. So here we're going to go ahead, set this equal to 0. And solve for x. How?
You could factor out x to the 1/3.
No, not that one.
Find the common denominator.
No. Factor, yes, factor. But which one? The smaller one. The smaller exponent is what you factor. Okay, you wouldn't try to factor out x to the 5th out of that, would you?
Um. Negative a half. Okay, go here. Positive 2 over 6, positive a third. Okay, I see that. Yeah. It's negative half. Let's see. From there. Alright, that looks better. Eight or negative 8. And I'm not plugging those in.
Try factor actually. Factor the smaller one, and a lot of times it's going to help you. So if I factor out x to the negative 2/3, remember that factoring means divide, right? Factoring means divide. Distribution means multiply, so factoring means divide. We're taking our first term, divided by the term we are factoring out. What happens when you have common bases being divided? You are now divided by the term we are factoring out. What happens when you have common bases being divided? You are subtracting exponents. So do this math in your head. 1/3 minus negative 2/3. You're actually adding 2/3 there. You're going to get x to the first power. Do you see what I'm talking about? You're going to get x to the first. So this right here gives you 8x. The reason is because you have 1/3 minus negative 2/3. That's 3. Oh, 3. That's going to be 8x.
Okay.
Minus, well, this one's easy. X to negative. Two-thirds, we pull the whole thing out, we get 1. Is that a lot easier to solve?
Yeah.
Oh, heck yeah. Yeah, this you'd be stuck on that if you couldn't factor. I mean, you're stuck. But here we now know that we have 2 factors being multiplied together that gives us 0. The zero product property says that either this one is 0, or this one, don't forget about that one by the way, or this one is 0. That means x equals 0, or x equals 1/8.
Oh.
What are those numbers called that we just found? What are those? Critical points or critical numbers. I think your book might use critical numbers. Critical points or critical numbers. That's what those state. Those are where you have the potential of having a horizontal slope, or I'm sorry, you do have horizontal slope. Potential of having relative max or relative min. Are you okay on finding that? The basic algebra, if you need help on that, you can come and see me. I'll show you how to factor out negative exponents. That should be in from your Math C classes or your intermediate algebra classes. Now, what do we do after that?
Plug it into the original function.
These two, and what else?
Already in points.
Endpoints. So do that. So here's our x values we're plugging in. We're doing -1 because that's an endpoint. We're going to do 0 because that was a critical number. We're going to do 1/8 because, hey, that was a critical number. And we're going to do 1 because that's another endpoint. Whichever one of these values is biggest, that's your absolute max. Whatever one of these values is smallest, that's your absolute min. And these are the places where they occur. I think I made that point last time. Go ahead and plug those in for me and find out what you get. Oh, how nice was I that I gave you 1/8, huh? We're so nice, cube roots. Oh, you love me now, don't you? No, admitted that far? Okay, you will love me. Get down here, you love me. let's see, -1. What'd you get, 9? Tell you what, I'll do this one for you guys, just because I'm a nice guy.
Yeah.
3. 16. What's 16 times 6?
96. 16.
So 90? Did I do that wrong? 96? Wait, for the whole thing?
Oh, no.
No, you have to subtract 6, I believe. Someone tell me what that is. You shouldn't be looking at me blankly right now. You should have a calculator and you should be working on it. Don't look at me blankly. Come on, if I can do that in your head, you have all calculators, you should be able to whip that out. Oh, you know, I did it wrong. I was wrong on that. I did with 8 and not 1 8. 6/16. Let's see here. Mr. Has. Yeah. -9? Okay, good. Okay, so somebody gotta be able to get those things. Which is the largest number that we attain? That is your absolute max. The absolute max is not -1, okay? That's just a place where on the x-axis where you get it. So this is your absolute max. It occurs at x equals -1. What's your minimum? That's the one, yeah. Absolute min, and it occurs at x equals 1/8. So let's do a couple more questions here, okay? Let's say that I did this. Do I still have an absolute max?
Yeah.
Absolutely, yeah. That's that endpoint, right? I didn't get rid of that endpoint. Do I have an absolute min?
Yes.
Min. Is that an endpoint? Then I still have it, that's fine. Absolute max? No, that's off the table right now. So the -1's gone. Okay, no absolute max. Absolute min?
Yes.
Yes, that's still there. Okay. So are you starting to see how the endpoints play a factor in what you're doing here? Now let's try one more. I want to find the absolute max and min on that function.
Is there only one? We're missing one. Could have missed one, I guess.
My question is, can I check this? Can I check it on that close interval?
No.
0 to 1.
See undefined.
Why or why not? So if I plug in 0, I would get a 0, right, on the geometer. That's not a good thing. If I plug in 1, I'll also get a 0 on the geometer. Do you see what I'm saying? So on this interval, I'm not going to have any endpoints because those are asymptotes at that spot. So I'm not going to have any. So I can't check this. Can I check this? No. No, I can only check the open interval. So, okay, well, how do we do that? Well, when we're doing something like this, it's not like you can plug in 1 and 0, right? Like the polynomials, you could just plug those in and see if they're getting bigger or getting smaller. You can't do that here, so what we're going to have to do is find first the critical numbers. That's what we do all the time. You with me? You find critical numbers, you set it equal to 0, you set their derivative equal to 0, that's fine. But then we're going to have to take some one-sided limits. We're going to have to find the limit of this thing as we're going towards 0 from the right, and the limit of this thing as we're going towards 1 from the left. That's going to give us where our function's tending. Now, stop for a second. Just think critically about this. You know that there's going to be an asymptote here and here, right? So this function is either going to be going way up high or way down low, and then way up high or way down low. So somewhere we're not going to have an absolute max or min, or both, we don't know. We just need the limit to tell us where it's going. It could be going like this, right? In that case, we'll have an absolute min, but not an absolute max. It could be going like this. In that case, we'll have an absolute max, but not min. It could be going like this or like this, in which case we're going to have nothing. You follow? So we're going to do that. Now let's go ahead and let's do that before we do the derivative, because if it's like this, we're done. That would be kind of nice, right? Can we do the limits first? So limit as x approaches 0, x approaches 1, zero, are we going to be going from the left or from the right to get to 0?
Yeah, from the right.
From the right. 0, 1. You're to get to 1. You're coming from the
Left.
Yeah. Now, let's do the limit. Is there anything to factor? Well, yes, there is. You can factor on x. Is there anything to simplify that x? So what you need here is a sign analysis. Remember the sign analysis that we talked about? So if you're talking about sign analysis, from 0 to 1, oh, you know what? We might need a derivative actually, because it's going to give us a separating point there. You can plug in a number really close to 0 and see what it's doing, a number really close to 1, but I do want you to check this out. Let's find the derivative and find our critical numbers and see how it plays a part here as well. It might not play a part. No, you know what? I doubt it. Plug in a number between 0 and 1. Would you agree that those are the only places where we actually have a problem? So at 0 and 1. So anywhere between there, between 0 and 1, our signs are all going to be the same, true? So we're going to be either all positive or all negative. That's going to be interesting. So we're probably going to be in one of these situations, all up or all down. We don't have a separating point here. The critical number won't give us one, actually. That's just for slow. I misspoke earlier, like 5 seconds ago. Keep track of that. The only time that happens. Kidding. Anyway, since we don't have a break between there, and that is our interval, these are all going to be either negative numbers or all going to be positive numbers. I'm guessing since when you square fractions, they get smaller, that this is probably all going to be negative. Is that true? So I plugged in a number between here. Since these are asymptotes, and we got negative the whole way across, true? Whether you plug in 0.1 or 9.999, you're going to get all negative numbers. That means our asymptotes look like this. I can guarantee you right now that we're not going to have what?
Minimum.
Min. We're not going to have an absolute min. Why not? Because it goes to negative infinity, for sure. Even if one side went to negative infinity, it still wouldn't have an absolute minimum. You okay? Which one will we have? Why? It's going to come up and it's going to go back down. That says on a continuous function, which this one is, in that interval, that's continuous. In that interval, that says I will have an absolute max there. How do we find it? That's where the first derivative comes in. So, right, do you understand this? This said, coming to 0 from the right gave you negative infinity. Coming to 1 from the left gave you negative infinity. Negative infinity is way smaller than any number you can find, so that means there's no absolute minimum. That's going to the same place. No absolute minimum. They don't have to go to the same place, okay? They go to positive infinity. But this just says that in both cases, you're not going to have an absolute minimum. Do you follow? If this one had magically gone to positive infinity, we'd have neither. If they both gone to positive infinity, we wouldn't have an absolute max, but we wouldn't have a min. You with me on that, the logic there? So find these first. That might be a great way to do it. Eliminate some of your problems, or eliminate some of your choices. We're not going to have an absolute min. Now I want you to find the first derivative. There's a couple options. You can move that thing up top and make it -1. You can do a quotient rule. hopefully you're able to find about the same thing. By the way, some of your negatives are nasty, all right? Some of you are ruining some of your problems based on your negatives, especially distributing your negatives on your implicit differentiation. So when you get that homework back, it's already graded, I've looked at it, but this is too much to pass around in one day, there's a lot of it. So when you look at that, check out I've circled your negatives, so you're just not distributing negatives. Be careful on this stuff. Like here, if you don't have that parentheses, you put a negative up front without distributing, you're gonna be wrong on that +1. Do you see what I'm talking?
Okay, I did that.
You're wrong there. So here, this
Or I
is
didn't do that.
definitely negative 2x plus 1 over x squared minus x squared. Show of hands, how many people will find that derivative? If you did the quotient
I
rule,
did.
you'll get the same thing. You just have to distribute, okay? And you'll get negative 2x plus 1. Did anyone do it that way, quotient rule? You got the same thing? Perfect. What do we do with our
What do
first
you do?
derivative
Always
in
pay
order to
attention. Product rule? You put -1. Did the general power rule.
So that we find our critical numbers, what do you set it equal to? So do that, set it equal to 0. Now, even though that looks really, really nasty, think about something. Just think. Where could this possibly be equal to 0? It's not where the denominator equals 0, because that's going to give you undefined points. In fact, that's just going to be 0 and 1 again, isn't it? So the only place it could possibly be equal to 0 is where the numerator equals 0. So when you're solving rational equations like this is, which you've done before, you just have to set the numerator equal to 0. And that, in this case, is very easy. Which, by the way, you remember when I had you do all the distribution on quotient rule, and you're like, oh my gosh, do we really have to do that? Can we just leave it in parentheses? No, because you have to solve it, right? So you're going to have to distribute it anyway. So you may as well do that. You're going to get negative 2x plus 1 equals 0. Subtract 1, divide by -2, x is 1/2. Show of hands, how many people feel okay on getting the x is 1/2? This row, are you guys okay on this? All right. Hey, x equals 1/2. Is that in our interval?
Yep.
You should check that, right? You should probably check that. So that's in our interval. That means with our interval, we are certainly, as I magically predicted, we're going to have some sort of a critical number there because we're down here, It's got to reach a peak at some point, at least one peak. How do you find that peak? Plug it in. Do I need to check my endpoints?
No.
Do I have any endpoints?
No.
We've already done that work first. We know that our endpoints, we're not going to have any. It's going to keep going down forever. So all you got to do with this, since you know it's going down forever, you know for certain that is going to be an absolute max. It's continuous. This is negative infinity, that's negative infinity. It has to go up, it has to come down since it is continuous. So you just plug in 1/2, whatever value that is, that's an absolute max. What'd you get? Anybody else get -1/4? You plug it into, well, not your derivative, right? That would just give you slope. Plug it into here. So is the absolute max 1/2 or is absolute max -1/4?
This is -4, isn't it?
-1/4.
Wait a second, it's actually 4.
It's 1/4 on the bottom.
Negative
over
4.
one.
-4 is -4.
Thanks, Scott.
Because I was just taking.
Whatever,
I was just plugging it into
It's all
the
good.
end.
It's all right. Reciprocated, you're going to get -4.
Yeah. I forgot about that.
The is the absolute max -4 or 1/2? It's -4. It occurs at x equals -1/2. So x equals 1/2. That's your absolute maximum for that function. Can you do it?
Yeah.
How many people feel okay with what we just talked about? So our ideas are, if you have one of these weird functions, man, and you can't plug in the endpoints, if you can't plug those in, if it's not a polynomial and you literally can't plug it in, do your sign analysis. You know they're going to be asymptotes, right? So we've talked about that. You know they're going to be asymptotes. They're either going to do this, this, or this. Right? They're going to do one of those things. Looks like dance moves. Anyway, that's what it's going to be. It's going to do this or this or this. I'm so awesome on the dance floor, by the way. So cool. Not really. Not at all. I'll do my calculus dance. So you know you're going to eliminate some of your choices here. So there won't be minimums and maximums in some cases. Then you find your derivative. Then you know what you have after that. Okay. If you get a minus and a plus, then you're done.
Yeah, you don't even have to do the derivative.
You're done. Those are nice problems. Those won't happen very often, but those are nice problems. Most of the time you're going to get this or that, otherwise the problem is kind of stupid, right? Yeah. Anyway. Do you have a good feeling about absolute maximum? If you have endpoints, you check endpoints and critical numbers. If you don't have endpoints, you check critical numbers and you do one-sided limits with sign analysis, and that's the basic goal. Now, I'm going to give you a rundown of Rolle's theorem in about a minute. Yep. We're not going to really be covering a whole bunch of section 3.2. It's a very cool, it's a good idea, but I can tell you that idea in about a minute. So here it is. Rolle's theorem says, if your function crosses the x-axis and then crosses the x-axis again, so like that, and it's continuous between those points. So it could do anything, but if it crosses here and it crosses here, and you know it's continuous between them, tell me something that absolutely has to be certain about your slope between these 2 points. Well, it's going to have a maximum. Sure, we'll have a maximum. But tell me something between this interval about the slope. Not absolute. I care about absolute maximum. We're over that. Past that. Tell me what the slope will be equal to at least one point between here and here.
0.
It must be. Because you're coming up and you're coming down, right? Somewhere, at least one point, you'll have a 0 slope. Does that make sense? That's what Rolle's theorem says. Hey, by the way, I'm going to draw a corollary right now. What's the slope of the x-axis?
0.
And that's the line that these 2 points cross, right? I'm going to show you the mean value theorem. The mean value theorem says take 2 points and draw a secant, AB. Would you agree that that secant line is going to have a slope? Okay, tell me something between these 2 points. If this is continuous, actually, let me make it stronger. If it's differentiable. That actually has to be differentiable because otherwise that eliminates sharp points, okay? So it's got to be differentiable. If that's differentiable, that's true. If this is differentiable, what has to happen at some point along this curve with the slope? Not zero.
Parallel.
What was it?
Parallel.
Good, parallel. What do you know about parallel lines? Okay, so would you agree that somewhere from here to here, this will have the same slope as this?
Yep.
Now, make the jump. Do you see that this is exactly the same thing as this? That's a special case. What's the slope of this line? Somewhere along there, it's going to have a zero slope. You get it? What's the slope of this line? I don't care, but somewhere along here, it's going to have a slope of that exact secant value. That's the Rolle's theorem and the mean value theorem.
So it's just a concept.
Well, you can verify it, but yes, it's just a concept. If f of x is differentiable, more than continuity, differentiable on AB, f prime of x will equal 0 for some point on AB. That must be true. And that's a fancy way of saying what I just said. You know what? This takes a little bit more work to write it simply, but would you understand that the slope of this would be bf of b? Well, the point is bf of b, and the point is a f of a. Then the slope is y2 minus y1 over x2. You know what? This takes a little bit more work to write it simply, but would you understand that the slope of this would be bf of b? Well, the point is bf of b, and the point is a f of a. Then the slope is y2 minus y1 over x2 minus x1. Are you okay with that? That that is actually the slope? y2 minus y1 over x2 minus x1? Then if f of x is differentiable on AB, the first derivative will equal that slope at some point. That's Rolle's theorem and mean value theorem. If you're required to check these, which I think some of your homework says that, what you would do is this. This is it. For mean value theorem, you find the first derivative, you set it equal to 0. You're going to get an x value, right? All you need to do is verify that the x is between a and b. It will be. If it's continuous, it will be. For this one, this is a little bit more tricky. You have to find the slope between the 2 points. You get me? Find the slope. This is the slope between 2 points. Take your first derivative, watch carefully. Take your first derivative and set it equal to the slope. You get me? Set it equal to the slope and solve for x.
Okay, instead of 0.
It's not 0, it's the slope.
Yeah.
And then verify that whatever point you get is between your interval. And that's all that says. It's a verification process, basically. So all in all, in plain English, this says if f of x crosses the x-axis and it's differentiable, at some point you will have a horizontal tangent. All it says. If f of x is continuous, at some point the slope of your function will equal the slope of your secant
Secant line.
between 2 points, if it's differentiable between those 2 points. That's all it says. Raise your hand if you feel okay with your roles and mean value. Sweet. Love that. Now, stuff that we actually can do, that is interesting, it really is. But stuff that we can actually do some things with. Specifically, we're going to get into some curve sketching, which
Okay, that's enough for the day.